there seem to be a lot of people with questions about, about this particular question in the written assignment, so I wanted to create a video to explain it more thoroughly. So in part A, I'm going to change the pen here real quick. The set W is the collection of all polynomials in P2. So I'm changing the notation here to match maybe more closely what you guys are seeing in my math lab. So collection of all polynomials in P2, which is polynomials of degree less than or equal to 2. So anything with terms up to, let's say, t squared. Such that, so there's this added condition in the set in A where the derivative at 2 must equal 0. The value of the derivative when x or t equals 2 is 0. So we're asked whether this is a subspace. So there's the theorem in your notes that says there's 3 conditions. We know we're dealing with a subset of one of the classic vector spaces, which collections of polynomials, that's one of our classic vector spaces. Then we don't have to go through all 10 axioms to show that it's a vector space. We can just prove the 3 conditions, which are, does it contain the 0 vector? Is it closed under addition? Which, to prove something is closed under addition, you'd have to say if I take 2 generic elements of the set, let's say P and Q, from W, and I add them, is that sum also an element of W? No matter what the P and the Q elements are, from just 2 generic elements, is the sum always in W? And then thirdly, is it closed under scalar multiplication? So if you take any number C times any polynomial from W, that product contained in W. Now with item 1 there, the 0 vector, what we call a 0 vector depends on the set that we're talking about. So in a collection of polynomials, or actually in any collection of functions, the 0 vector is just the constant function f of x equals 0. So constant functions are technically polynomials. It's a degree 0 polynomial. But this would also be your 0 vector in just any collection of functions on R1. Okay, so we want to determine whether this function is contained in the specific set W that's contained, that's described in part A, which is to say, okay, so is the degree less than or equal to 2? Yes, because it's a degree 0 polynomial. And is the derivative when x equals 2 equal to 0? And yes, that would be true because the derivative of any constant function is always 0 for every value of x, so that's certainly true. So the set A does contain the 0 vector. So secondly, if we take any 2 polynomials from this set W, which what we can assume then is that the derivative of this polynomial P at 2 is 0, and the derivative of this polynomial Q at 2 is 0. We can assume that that's true at least, because that's the requirement if P and Q belong to W. So now the question is, does P plus Q belong in W? And it kind of goes without saying that the sum of 2 polynomials of degree less than or equal to 2 will be a polynomial of degree less than or equal to 2. So I wasn't expecting that you guys would all necessarily prove that. The real condition that we need to verify is this added condition, is the derivative at 2 equal to 0. And it is, thanks to a property of derivatives, whoops, I'll put the P first, that when you take the derivative of a sum of 2 functions, we can just take the derivative of the 2 functions individually. So this is equal to P prime at 2 plus Q prime at 2, which then we have 0 plus 0. So sure, that sum is 0. So this set is closed under addition. Thirdly, scalar multiplication. So if we let C be any number times some polynomial from W, P, and we check, is the derivative at 2 equal to 0? Well, again, thanks to a property of derivatives, when you take the derivative of a scalar times a function, we can just move that scalar outside, right, and take the derivative of the function on its own. And so then this would be equal to c times 0. If p is an element of w, then the derivative at 2 is 0. And so no matter what the scalar is out front, we're multiplying by 0, so that product is 0. So yes, the collection in A does meet all three of these requirements. So this collection is a subspace of P2. Now with B, I'm actually going to try to squeeze this in right here. I'll mostly just discuss B. B actually fails all three of these requirements. So the 0 vector with regard to P2 is the f of x equals 0 function, the constant function. If the requirement now with B, and let me write out the set W for part B here. So it's this collection of all polynomials in P2, but this time the added condition is that the derivative at 2 is 1. And so that's going to fail for the function f of x equals 0, the derivative everywhere is 0. So with the set B, I'll make a little column here for the conditions for part B. No, it does not contain the 0 vector. And so that's enough. You could actually stop there and just say no, it doesn't contain the 0 vector. But also, if you take the sum of two, if you have P and Q and W, and you take the sum of those two functions, and then take the derivative at 2, now you're going to have P prime at 2, which is 1, plus Q prime at 2, which is 1, so we get 2. So the sum, P plus Q, does not belong to W for part B. And thirdly, if you do C times a polynomial P in the collection that's described in B, and you take the derivative at 2, you're going to have C times 1 now. And that's equal to C. And C can be any real number, so it certainly can be something other than 1, in which case it's not closed under scalar multiplication either. Because when you take a scalar times a polynomial in this collection here, the product is going to be equal to that scalar C, which is probably not 1. So it fails all three. You really just have to show one of those because since the requirement in that theorem says if the subset satisfies all three of these conditions, then it's a subspace. So when it fails one of them, then that's it. It doesn't satisfy all three conditions, so it cannot possibly be a subspace. So you do not in B need to go through all three of those conditions. You just have to show that any one of them fails, and they do all three fail in part B.